Hi, I'm Mallikarjun. So now I'll present the section on faces. Let's see why we want to address faces separately. So to start with, um, so faces do not have that many articulations as compared to humans, and they also have a regular pattern. For example, they are like vertically symmetric, and there are fixed number of parts. It's also less diverse. For example, it does not have any clothing involved, less accessories, and because of the number of applications it has, there's large amount of data available. So as a result, it's easier to build prior models compared to other objects. But yeah, it also has challenges. For example, it involves modeling hair, which has complex geometry, and the topology also varies across different hairstyles. Even like a minor misprediction in the geometry could lead to a perceptually significant difference for humans because we are well versed with that. But yeah, like face has like a lot of applications in AR, VR, movies, gaming, and also. Sorry. Ah, sorry, I did not read that. Okay. So broadly, the methods for faces can be categorized into two different problem statements. For like given a single image, can we reconstruct the whole geometry of the face? This is possible because we can build prior models. And there are also cases where if you want like high quality model for faces, for a person specific model, there are methods which can take monocular video as input and can build like high quality models, which also has editing applications. Yeah, so the methods can also be broadly categorized based on the type of representation of the data. So one set of methods use like explicit representation, where, for example, mesh-based representation, which has fixed resolution and topology. As a result, and this type of methods have been extensively studied in the past and currently leads the charts in popular benchmark, at least for the face region. The difficulty is that it's hard to model thin structure and objects such as varying topologies such as hair. So on the other hand, we have methods that rely on implicit representations, which can represent like different topology. As a result, it's easier to model hair with this sort of representation. The disadvantage is that it's not as efficient as explicit models. Let's look at explicit morphable models a bit closely. Yeah, so typically the data is represented by a fixed number of vertices, and they also have color associated with that. To build a pair model, people generally collect a lot of 3D scans. And then if you also want to learn a pair for expression space, you have expressions involved in the data. And these data are densely registered against each other to build, to have a set of scans. And these methods typically do some sort of low dimensionality reduction. For example, in the case of Blance and Witter, they use principal component analysis or tensor decomposition, as in the case of multilinear model. And lately, there have been methods which use nonlinear representation. The recent two surveys extensively talks about these methods, and here we only try to address methods that are recent. So basically, once you have like to solve the problem of getting the reconstruction from a single image, typically it involves optimizing for these set of parameters. Apart from the parameters for the shape, expression, and albedo, these methods also try to optimize for the rigid transformation and parameters for elimination model. With the help of differentiable rendering and a optimization function which looks like this, which involves a data term which is like sparse landmark term and a dense photometric term. And they also have a regularizer which constrains the space of parameters to stay in the valid region. And this can be solved iteratively, or you can train an encoder to directly regress these parameters. Focus is one such method which was recently proposed, where they learn an encoder to regress these parameters directly. Along with that, they also try to regress outlier pixels for which the model cannot define such pixels. For example, cap in this case cannot be modeled by the prior model. By solving for these two tasks together, they can train an encoder which can have better accuracy compared to not doing that. Most of the encoder based training methods are done in a self-supervised training without having any paired 3D data. This inherently has ambiguity because of perspective projection. For example, a fixed size face can get projected to two different sizes on image plane because of perspective projection. So this method proposes a simple way of solving this by using paired data along with some transfer learning trick. They were able to generalize to novel test identities. And surprisingly, this leads the charts on popular benchmark. So the methods we just saw were like generic and they are not person specific. If the application deserves a high quality model, so Brassel et al. Recently proposed a method which can learn high quality explicit models from monocular video. So they start with 3D reconstruction and they learn a delta space on top of these vertices to account for regions which is not addressed by 3D for example, hair and other details. And they also have an extra application of editing expression. Let's now look at methods that rely on implicit representation. So this again can be broadly categorized based on the type of supervision which is used to build these priors. One set of methods uses supervised training, which basically has some reconstruction loss. The advantage in this sort of methods is that you can disentangle identity and expression space. The disadvantage is that they tend to have poor latent space and doesn't generalize that well. On the other hand, we have methods that rely on purely adversarial training, where they just learn from 2D data. These tends to show good generative capability, and the quality of the metric quality of these models depends on the camera pose distribution assumed to train these models. Typically, methods that rely on supervised training follow autodecoder sort of a training strategy, where they have a set of random latent vectors initialized over the course of training. Latent vectors for each of the training sample. Over the course of training, they try to optimize for the neural network parameters and also the latent codes using reconstruction loss. And once the training is done, they use this neural network to get the priors for reconstruction later. One such method is headnerf, where they extend the strategy to have like two sets of latent vectors, for example, identity and expression. Because they are trained on data where they have multiple identities performing same expression and each identity performing different expressions, they can enforce such constraints in the latent space to disentangle the identity and expression. Because this is parameterized by a neural network, which has higher capacity to high capacity, to regularize the latent space, they use estimated parameters from explicit 3D models to regularize the latent space. Morphanerf and Morph also follow a similar strategy with one where Morphanerf tries to learn it in a feed-forward manner with shape directly estimated using explicit 3D whereas Morph extends this approach by also regressing diffuse and specular components, which is necessary for some relighting tasks. Let's look at methods that rely on adversarial training. So it typically has this sort of schematic representation where these methods use neural network to regress the whole 3D scene in some sort of representation conditioned on a latent space. They also assume a distribution of camera pose for a given set of 2D images they have. So over the course of training, this sample the latent space and synthesize the scene. And the scene is rendered using the sampled camera pose for each iteration. And once you have the rendered scene as an image, and this image is supervised using only discriminator loss, using unstructured 2D data. There have been many methods in this category, which uses different types of network architectures, MLP, 2D CNN, and 3D CNNs, based on the type of representation. The first set of methods used nerve sort of a representation to regress the volumetric space using an MLP. But it is expensive to query an MLP at every point in space. To solve the sampling problem, recently proposed Graham tried to parameterize the space using a bunch of 2D manifolds instead of the whole scene. This enabled them to have a bit more high accuracy renderings. But this still required them to query the MLP every point in 3D space. Recently proposed EG3D tried to overcome this problem by regressing the whole scene all at once, which is parameterized by a triplanar representation, which can be efficiently obtained using 2D CNNs. To have like much more 3D accurate representation, there are also methods that can regress voxel grids directly using a 3D CNNs as well. Yeah, so in this slide, we can see the importance of type of supervision used to learn the prior models. For example, here you can see interpolation results between the samples for each of these methods. Head nerve and lower nerve is trained in a supervised manner, in an autodecoder manner, with one difference being head nerve latent space was regularized with explicit 3D parameters. This allows them to have a much smoother interpolation compared to lower nerve. On the other hand, we have EG3D, which was trained purely in an adversarial manner, which seems to have much more smoother space with higher quality models. So once you have this implicit models learned, typically reconstruction involves basically given an input image. These methods try to optimize the latent code while keeping the neural network fixed. And some method also try to fine tune the parameters of the neural network to get much more details. So here are some comparison results across different categories. For example, 3DMMs, it's hard to model hair. Head nerve, which is trained on supervised training, tend to not generalize well for novel test scenes, whereas EG3D, which is trained on adversarial manner, seems to get high quality details when including hair. Similar to explicit models, there are also methods that rely on implicit representation to get high quality 3D models for person specific models given monocular video as input. They again use explicit 3D models to get the pose information and learn the rest of the information in implicit representation. Here in this method, they use expression condition neural network to model the deformations in a naive implicit manner. IM Avatar and RigNerve also follows a similar strategy, but with one exception that they explicitly model the deformation of expression explicitly. Because of this reason, they can get lesser artifacts while null video renderings. To conclude, we see explicit models tend to suffer with complex topology and has difficulty in getting finer details. And implicit models that were trained on supervised training are tend to have poor generalization capabilities, whereas implicit models which were trained in an adversarial manner tend to have good quality models, but metrically the metrical accuracy depends on the pose distribution assumed during training. And also we haven't seen a method implicit model based methods which are trained in adversarial manner that makes use of video dataset, which could help in getting much more better deformations and also disentanglement. So it might be interesting to watch out in this field as well. Thank you.